This is part 3 of lecture 1 of linear algebra. And this is the most important part of this lecture because this part is about matrices. What are matrices? An m times n real matrix consists of m times n real numbers, aij, which we usually put as a grid like this with m rows and n columns. And we often also put brackets on the left and the right hand side of this grid. There's a special, very special and very important case when m equal n, when the number of rows and number of columns are the same. In this case, we say that this matrix is a square matrix. And if all entries of a matrix are 0, in this case, we say that this is a 0 matrix, and we usually, for simplicity, denote it simply by 0, similarly what we did with vectors. If you have square n times n matrix such that all its entries are 0 except diagonal, and on diagonal you have 1 everywhere, we say that this is identity matrix, n times n identity matrix. You will see later that identity metrics are very important and they're very handy. Okay, now we defined what matrices are. Let's define some operations on matrices, algebraic operations. However, before doing this, let me basically introduce one shortcut, very handy notation, which you probably already met somewhere. This is basically a shortcut for the sum. If you have n real numbers, a1, a2, an, you can write the sum as a1 plus a2, blah, 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 plus an, or you can basically shortcut it like this, like sigma. It's a Greek letter, capital sigma, which stands for summation. Yeah. So this shortcut for the sum of a1, a2, a3, up to an. Yeah. So let's illustrate it by an example of one matrix. If we take m times n matrix, we can consider sum of all its elements. We can compute the sum in two different ways. So first, we can actually add all elements in each row, and then we take resulting sums and add together. Yeah, and we get sum of all elements of a matrix. Or we can first take a sum of all elements in each column and then add resulting sums together. Of course, we're going to get the same number. This can be expressed in this lengthy formula. So on the left-hand side, it's what I just did in the beginning. I take all sums of all elements in each row and then add them together. On the right-hand side, it's the same thing with columns. Of course, this is the same result. So this is why I have equality here. And usually in such cases, we say that we changed the order of summation. You will see this pattern many times in the future when we compute some sums and want to prove some formulas. Okay, now let us introduce a few basic operations that we can do with matrices. We fix a matrix A, we denote by aij, it's ij entry, so it's entry of this matrix in the row number I and the column number j. Okay, and if you have two matrices A and B of the same size, of course, m times n, you can add them absolutely in the same way as we added vectors. You added corresponding entries and you form a new matrix out of this. So yeah, this is absolutely the same as we did with vectors. Similarly, if you have a real number C, you can multiply your matrix A by this number C. So basically, if you want to multiply a matrix by a number, you just multiply all its entries by this number. Absolutely like we did with vectors. So far, nothing new. It's very similar to what we did with vectors already in the part 2 of this lecture. Now we're going to define something very new. So now we have two matrices, A and B, whose sizes not the same, but they match to each other. So let's fix matrix A, m times n, matrix A, so m columns and m rows and columns. And let's fix matrix B, which is n times p matrix. So it has n rows, p columns. Now, if you have these two matrices, you can form a matrix AB called a product of these two matrices, whose size is m times p. It has m rows and p columns, such that its entries, ik entries, can be computed using this formula. This formula may look a little bit complicated, so let me for a second actually get rid of the sigma notation for the sum. So this ik entry of AB is the sum. Yeah. If you look at this, you see what's going on. You take ith row of the matrix A, and then you take kth column of the matrix B, and then you take the dot product. If you imagine that this ith row, if you rotate it like this, so you get a vector, and these two vectors, ith row of the matrix A and the kth column of the matrix B, they live in the same space, Rn. They have the same number of entries, so you can take the dot product, and this is it actually looks like a formula for the dot product of these two vectors. Yeah, so you get a number, and you put this number as an ik entry of the matrix AB. Okay, this may look a little bit technical, and it is technical. And the only way to get used to this is basically practice. You have to multiply a lot of matrices until you feel comfortable with multiplication of matrices. You should do this basically automatically. If I give you a couple matrices whose sizes match for the multiplication, you should be ready immediately multiply them without thinking. So otherwise, if you think when you multiply matrices, it's a bad sign. It's like thinking when you multiply numbers, small numbers. Yeah. So I strongly suggest you to take few matrices of small size, like 2 times 3, 3 times 5, and multiply them and see what's going on. This is actually a good experience, and this experience gonna help you to get used to matrices. Okay, so now once we define these operations, let's derive some properties of these operations, basically using only these definitions on this slide. Okay, few basic properties are very similar to what we already did with vectors. So, for example, if we add matrices, this operation is associative. It basically means it doesn't matter where we put brackets, in which order we add them, A plus B plus C, we can first add A plus B and then add C, or first add B plus C and add A, it's going to be the same. Again, it follows immediately from the formula for the addition of matrices. Yeah, but you have to check this. We don't have time to check this during this lecture, but you have to check this by yourself. It's a good exercise using only a formula on the previous slide. Of course, similarly, A plus B is B plus A, basically because addition of numbers is commutative, so you have the same for matrices. If you add zero matrix to any given matrix A, of course, you get matrix A. So here, A is a matrix, zero, it's a zero matrix. It's not a number now. Again, sorry for the confusion, but this is just traditional notation. Yeah, so A plus zero is A for matrices. Yeah. If you multiply sum of matrices by a number, again, you apply the same rules as for vectors. Yeah. Okay, the last property here, it's actually already a little bit new because we use multiplication of matrices. And what does it tell you? It tells you that if you have m times n matrix A, and you have n times n square identity matrix, you can multiply A and I in this order: A on the left, I on the right, IN on the right. And you get A. You have to check this. You have to check accurately by yourself, maybe for small m and n, that you're going to get A. This is very important. Similarly, if you take m times m identity matrix, you can multiply its and matrix A in the opposite order. I am on the left, A on the right. And again, you're going to get matrix A. This means that identity matrix behaves very similar like 1 in real numbers. So if you multiply 5 by 1, you get 5. Yeah, if you multiply 6 by 1, you get 6. So especially this property becomes especially important if m equal n. If m equal n, then you can shortcut it like ai equal ia equal a. Yeah. Okay, so far so good. Let's list a few more properties. Let's see how addition and multiplication can be combined together. This has to be done accurately, because when you multiply matrices, the sizes have to match. So, to be precise, let's fix two m times n matrices, A and B. In this case, we can add them. And let's fix n times p matrices, C and D. In this case, we can add them, but also we can multiply A times C, A times D. We can multiply B times C, B times D. Okay, then we have this few very clear properties. For example, A plus B times C is the same as AC plus BC. Again, you have to check it accurately using the formulas for multiplication and addition, which were listed on the previous slide. Don't trust it. Don't believe me. Check it yourself. This is the best way to practice, to get used to matrices. Check every property on this slide by yourself. Okay, of course, we can write similar property for when you multiply A and C plus D. And of course, you can replace here A by B. It's going to be the same. So A times C plus D is the same as AC plus AD. Okay. And finally, if you have two matrices A and D, in this case, which you can multiply, you can have A times D. It's a matrix M times P. Its size is M times P. And if you multiply it by a constant, you can do it in several different orders. So first, you can multiply AD, and then you multiply it by a scalar, by this number C. Or you can multiply matrix A by C, and then multiply by D. Or you can multiply C by D, and then multiply by A on the left. Yeah, in all these cases, you get the same matrix. Again, all of these properties has to be checked. But this is probably not the most important property about matrix multiplication. The most important property about matrix multiplication, and basically sort of like miracle, is the next one. So if you have three matrices, A, M times N, B, N times P. If you multiply them, you get a matrix M times P size. Now you can multiply this matrix to another matrix C, whose size is P times Q. So resulting matrix is going to be P times M times Q. So, but you can do it in two different ways. First, you multiply AB times C, like I said, but you can also first multiply a matrix B times matrix C, and then you're going to get a matrix of size N times Q. And then you can multiply it by the matrix A on the left. So you're going to get two different, a priori different matrices, AB times C and A times B times C. And the main property of this multiplication of matrices tells us that this is the same matrix. These two different ways give you the same result. Basically, this means that this multiplication of matrices is associative operation. And this is very good. It basically means when you multiply matrices, we don't need to remember where to put brackets. Results going to be the same, always. This is super handy. Okay. And probably among all properties listed on the slide, this one is the most complicated to prove. So let's briefly explain how to prove it on the next slide. So we want to check that AB times C equal A times B times C. But basically, this means that we have to check equality of entries, of that each entry, IL entry on the left matrix, it's equal to IL entry of the right matrix. Okay, if we do this, then it's fine. Now we have to accurately rewrite formula for the entry of the left matrix and formula for the entry of the right matrix using twice formula for the multiplication in each case. So basically, we have to apply this formula for multiplication 4 times to compute AB and then C, and then BC and then A. Okay, this is done using this summation symbols here in these two lines. I know it looks ugly. Unfortunately, I couldn't make it simpler, but this basically computes IL entry of each of these metrics. Yeah, and you have this terrible sums, but then you observe that we can change the order of summation. You change the order of summation in each of this formula, and you see that they are the same. Okay. A little bit later, we will get another way how to prove this formula without such complicated summations. But I strongly suggest to check this property, to check this proof, and to check this property in some cases. Take three matrices, random, of course, that whose sizes match. Say 2 times 3, 3 times 4, 4 times 2. Multiply them in two different ways. Convince yourself that you get the same result. And while you're going to do this, you will basically see the proof on this slide. It's going to be a good illustration for this proof. And then try to go through the proof and try to repeat the proof. Explain this proof to some of your friends and maybe read it one more time. This is important. We have no time to explain this in more details. Please refer to the lecture notes or the book for more detailed explanation. Okay, now let me describe one very important observation how one can look at a matrix. You have m times n matrix, yeah. So you can always look on this matrix as a collection of n columns. Where these columns lives? They live in Rm, yeah, because each of this column has m entry. So this is ordered list of m real numbers. So this is element of Rm. So you can informally write in this course and in the lecture notes, we're going to, in this case, write like this. So A equal x1 vertical bar, x2 vertical bar, blah, 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 vertical bar xn. So where x1, x2, xn are first, second, third, and nth column vectors of A. Okay. So, for example, if you take A11, A21 up to AM1, this is just the first column of your matrix. We call it X1. You can consider this as a vector in Rm. And at the same time, you can consider this as a matrix of M times 1 size. Yeah. And you know that you can multiply A times X1. Yeah. Good. So also, if you take your matrix A, and if you take some vector y in Rm, you can multiply A times y. So first observation, that if you multiply A times y, you're going to get the sum. y1 times x1 plus y2 times x2 plus yn times xn. Again, here, y1, y2, yn are numbers. And x1, x2, xn are vectors, NRM. So a little bit later, you will see that this sum is called linear combination of vectors x1, xn. So again, multiplying matrix A by a vector y gives you linear combination of its column vectors. This is actually very useful. This is mega useful. You will see it later. Vice versa. If you have p vectors, y1, y2, yp, that lives in an n-dimensional space, Rn, that lives in Rn, and you can form a matrix out of them. You put these vectors as a column vectors, and so you get the matrix of n times p size, n rows, p columns. And then what happens if you multiply A times this matrix, A on the left? And then it's basically the same as to multiply each column by A. So this is actually also super useful. If you have two matrices A and B, So in this case, this is B. So multiplying AB is the same as multiplying A and each column of matrix B. So this gives you very easy way how to remember how to multiply matrices. So the only thing you have to basically remember how to multiply matrix and the vector, which of corresponding sides. Okay, again, this is a bit maybe too fast, and this is maybe again a bit too new for you, but you really have to get used to this. Without getting used to this, it's very hard actually to digest the material of linear algebra. Okay, so we will go back to this observation on this slide several times in the future. I will actually insist of using this because it simplifies a lot of proofs. You will see later. First, let us ask one easy question. We know how to add matrices, how to subtract, how to multiply. Can we divide? Okay, let's check. Okay, first of all, it's sort of easy to observe that if you want to divide matrices, it's better to do for square matrices, because for non-square matrices, it's going to be a math. So for simplicity on the slide, let's consider only square matrices. And again, square matrices are the most kind of useful, nice, and beautiful matrices among all other matrices. Okay, but of course, not every matrix is a square matrix. Anyway, on these slides, let's all matrices be square matrices. The set of all n times n matrices usually denoted by this M and R. So R explains that all entries of this matrix are real numbers, and n is number of its columns, number of its rows. Okay. First of all, sum of two matrices in this set, of course, it's a matrix in this set. Yeah, sum of two n times n matrices is n times n matrix. Moreover, product of two matrices in M and R is a matrix in the same set, because product of two n times n matrices is n times n matrix. So the set looks like set of numbers. You can multiply matrices and you get element of the set. You don't need to worry about that the sizes match. Any two matrices in this n times n matrices you can multiply, you can add. So this is a nice set with a nice operation. Frankly, my favorite set. Yeah. Now, the only thing we don't know, can we divide them? If we can divide them, it basically means it looks like real numbers. Unfortunately, we cannot always divide them. This is basically example. So suppose I have a matrix 1, 0, 0, 1. This is identity matrix. And suppose I have a matrix 1, 1, 0, 0. And I want to divide these matrices. I'm not sure I can do this, but suppose I can. So basically, what does it mean I can? It means that this ratio is a matrix. It's some matrix, n times n, such that if I multiply it by 1, 1, 0, 0 matrix, I get identity. I get this. It's basically just a definition of what division is. Okay, suppose this is true. Such matrix exists. Then, if I multiply it by matrix denominator 1, 1, 0, 0, and I can do it in two different ways. So first of all, let me multiply by this guy and multiply by this matrix. And look, this matrix 1, 1, 0, 0 and 1, 1, 0, 0, it should cancel, and then I get identity. And identity times any other matrix, it's the same matrix. So then on the left-hand side, I have to get this. Yeah. Assuming this division exists. On the other hand side, I know already, we already proved that the multiplication of matrices is an associative operation. So I can put these brackets in different order. I can put them here and here. So then I can rewrite the same product like this. And then I say, okay, but then I know how to compute these two matrices. Yeah, I just can compute them. And suddenly I observe that if I multiply this matrix and this matrix, I get zero matrix. You can check for yourself. This is good exercise. 1 times 1 minus 1 times 1 gets 0, 1 times 1 plus 1 times minus 1 is 0, and here you get zeros, get 0. But it's easy to see from elementary properties of this multiplication, from the rule how we multiply matrices, that 0 matrix times any matrix is 0. Yeah, this is immediately follows from the definition of multiplication. So what happened? It happened that we must get 0, 0. So, but these two matrices, 0, 0 and 1, 1, minus 1, minus 1, clearly they're different. They're not the same. So it means we have a problem. And the problem is that we cannot divide identity matrix by 1, 1, 0, 0. Such matrix just does not exist. So we cannot always divide matrices, unfortunately. Okay, but some of them we can divide. If we can divide them, we call them invertible. So invertible matrix, by definition, is a matrix, it's a square matrix, n times n, such that there exists another n times n matrix B, such that the product AB and BA is identity. This is definition. Again, let me repeat, the matrix A is called invertible if there exists a matrix B such that AB equal BA equal identity. And matrix is called singular if it's not invertible. Yeah, not every matrix is invertible, as we already saw on the previous slide. But one can show that if matrix A is invertible, that this matrix B such that AB equal BA, it's unique. And of course, intuitively, it's called its inverse. Yeah, it's called, and usually it's denoted as like A to the power of minus 1. Yeah, okay. Later, you will learn formulas for the inverse of every square matrix, for which inverse exists. Yeah. The set of all invertible n times n matrices traditionally is denoted by this symbol, GLNR. GL stands for general linear. N is a size of matrices, n times n, and R says its entries of these matrices are real numbers. So it's called general linear group of n times n invertible matrices. Okay, let's consider one very explicit example, 2 by 2. 1 by 1 is just numbers, so this is not maybe very interesting. 2 by 2, it's first new example. In this case, we can say everything about invertible matrices. We can actually find a formula for the inverse of every matrix. So if you have 2 by 2 matrix, A, B, C, D, if AD minus BC is not 0, then A is invertible, and its inverse is given by this formula. It's a very good exercise to check that this matrix is indeed inverse of matrix A, B, C, D. How to do this? Just multiply and check that the resulting matrix is identity, 2 by 2 identity matrix. You will see a little bit later that the number AD minus BC is called the determinant of the matrix A. Probably you already met, some of you maybe already met determinants in school. And then you will find, you will see the formula for the determinant 3 by 3, and you will see an inductive formula for the determinant of n by n matrix. We will do it later in a couple of weeks. Okay. This is an example. You can just take one matrix, 1 minus 2, 3, 5. You check this formula. You check its determinant. Its determinant is minus 1. And then you use this formula to find its inverse. You multiply and you check that it's indeed 1, 0, 0, 1. And then you check that if you multiply them in the other direction, you get identity matrix again. Important observation and remark and warning. Multiplication of square matrices is not commutative. If you have two matrices AB, both n times n, AB and BA often not the same. Sometimes they may be the same. In this case, we say that matrices commute, but quite often they are not the same. So be prepared to this. Okay. Another important thing which you can relate to any matrix is its transpose. So if you have m times n matrix, you have m rows and you have n columns. The transpose of matrix A is n times m matrix, denoted like a to the power of t. It's basically said A transposed, such that ij entry of the matrix A is a ji entry of the matrix A transposed. So basically, this means that you swap rows and the column. Every row you just rotate by pi over 2 and you put as a column, and vice versa. Every column you rotate and put as a row. That's it. Let's give an example. 1 minus 2, 4, minus 3, 5, 6. We transpose it. You put the first row, 1 minus 2, 4, you put as a first column. You put the second row, minus 3, 5, 6, you put as a second column. Okay. This is very handy. Sometimes it's very handy, very useful to swap from rows to columns. You can do this by transposing the matrix. This is absolutely standard notation in every book that uses matrices. You can see transpose of at least one matrix. This is just a rule. Okay. Now, few properties of the transpose of a matrix. Transpose of a sum is sum of transpose. Transpose of a product of two matrices, it's a product of transpose taken in the opposite direction. AB transpose, it's B transpose times A transpose. Of course, if sizes of this matrices match. And then if you transpose a matrix and you multiply it by a number, it doesn't matter in which order you're going to do this. And of course, if you take transpose twice, you get the original matrix. But this is, I think, is clear. It's quite important to check all of these properties by yourself, as we don't have basically time to check accurately these properties here. This is done in the lecture notes or in the book. Please do this yourself, at least in some examples. Practice, it's very important thing. All these matrices, materials, all the properties, this is all very new for you. So please practice as much as possible. Okay, in my opinion, the most useful property is number 3. AB transpose, it's B transpose times A transpose. Okay, and finally, before I conclude this lecture, let me mention two very nice types of matrices, which should a little bit reminds you symmetric, like even and odd functions. It's called symmetric and skew-symmetric matrices. Basically, if you have a square matrix, it's said to be symmetric if A is equal to its transpose. So basically, if you swap rows and columns, you still get the same matrix. You cannot define this for non-square matrices clearly because the number of rows and columns are different. But for symmetric, for square matrices, A transpose and A both have the same number of columns and rows. So this condition, A equal being equal to A transpose, this means matrix is symmetric. This is example. If you look at this example, it's clear if you what does it mean for the square matrix to take its transpose? It's basically you flip the entries of the matrix around the diagonal. Just swap the matrix around the diagonal, like reflection in diagonal. So if you reflect this matrix in diagonal, you're going to get the same matrix. Yeah. So it means it's symmetric. Symmetric matrices plays important role in mathematics. One of the most important results of this course is about symmetric matrices. It's basically one of the last big theorems in this course, which we're going to do in week 10. It's about symmetric matrices. So you really have to know what symmetric matrices are. Matrix called skew-symmetric. If you transpose it and you get minus original matrix. So this is less common. In this course, you're not going to see it quite often, but they plays also a very important role in mathematics. So it's good to know what they are. And also one of the exercises in tutorial, it's about symmetric, skew-symmetric matrices. Anyway, just know what they are. This is example of skew-symmetric matrix. You see, if you swap it around diagonal, if you reflect in diagonal, you get basically minus original matrix. And of course, on the diagonal must be 0. Why? Because if you have an element on diagonal, when you kind of reflect it, when you transpose, it's going to remain on the same place. So it must be equal to minus itself. So it must be 0. Okay, let me conclude this very important lecture. And okay, please go through all main properties of matrices and check them at least in some cases. Okay.